So let's get started. Welcome to our webinar, Model-Based Testing for Embedded Systems. I'm Thomas Schütz. And just to mention that if you have any questions, please put them in the sidebar under Fragen or questions. And I will answer them after the webinar via email. So let's get started. Topic today is model-based testing for embedded systems. So the first question is, why do we want models in development for embedded systems? In general, a model helps me to raise the level of abstraction. That's one of the main purposes of models. And yeah, I'm going to give you an example, not from the field of embedded systems or software development, but we want to count matches. So if you count those matches, takes a long time, and yeah, you're never entirely sure whether you got the result right. So if I ask you how many matches do you see, usually the answer is 50 or 100 or 70, something like that. The problem is you cannot count them because they're not arranged very well for counting. So if I arrange them a little bit different and I introduce a pattern, I raise the level of abstraction, I give a certain order to the chaos, and suddenly I can count them. So in this case, we see it's 123 matches. It's the same number. Doesn't look like it, but it is. And what happens here is, by rearranging the matches to a certain pattern, I reduce the liberty of geometric position. I reduce this to a very strict pattern. And by this reduction, I raise the level of abstraction, but only for a certain purpose. The main purpose here is to count the matches. If you have any other purpose, maybe you need another view, you need another abstraction for that. So if you have a look at a real world software project, it looks more like this. And to prove this, I generated a UML diagram, a flat UML diagram from a bigger motor control project. And as you can see nothing. So that's an entity relationship model of all your objects, or with all the relations and so on. It's really not very helpful to have a complete view of everything in one picture. So you need an abstraction to really understand what's going on here. So it's a good designed project. The problem is it's a wrong view. So how can we now raise the level of abstraction in our software projects? One thing is important to understand. The main purpose of models and model-driven development is to raise the level of abstraction and to raise the level of automation. If you only raise the level of abstraction, you decouple usually from your code. So I'm going to give an example. So let's assume you want to produce an executable for your embedded system. That's a hex code of an STM32 project. So that's something the processor understands really well and can execute directly. So, but for us as human beings, it's really hard to understand because there are a lot of details in it, and there's no abstraction for a human being in there. So that's why we have high-level programming languages like C, like Java, and so on. With C, we can describe what or how the program is supposed to work. So step by step, what it's supposed to do, and so on. And here we can already see it's a level of abstraction. We're talking about states, about switches, cases, and so on. So there are some higher level concepts than assembler or a machine code. So, but if I really want to express what I want to do, I could do this with a state machine. A state machine is a much higher level of abstraction. In the state machine, I already can see, okay, it seems to be a blinker. So it turns something on and off. After a certain time it's on, after a certain time it's off. So that's what I want to do. So model level is what I want to do. C program would be how do I do it? And the executable is how do I explain it to my processor, to my microcontroller, which needs much more details than a human being. So I'm raising the level of abstraction from the executable to the C program by leaving away the details of the microcontroller, from the C program to the model by leaving away the how do I do it step by step. And in the end, in the model, I explain what do I want to do. The problem is, in the end, I need the executable. So, and we can do this by using a code generator from model to C program and a compiler from the C program to the executable. And by that, introducing automation. As you can see, the model to C and C to executable, it's all the same. It's a generator, and the compiler. So compiler is nothing else than a generator, and a generator is nothing else than a compiler on a different level of abstraction. So that's important to understand. If you leave away the abstraction path, you have to work on a level of executable. If you leave away the automation path, you can work on model level or on C level. The problem is you do not get the result, the executable. So you need both directions to really work with model-driven development. So that said, let's focus on the testing. We're talking about model-based testing. First, I want to introduce the different levels which we can test. So the first level will be a unit test, so single C module, classes, Java class, C++ class, or whatever it is. That's a unit test. I can also use a unit test framework for a software integration test usually. So if I bring together several software units, I can write a software integration test. If it's not asynchronous software, then you get away with a regular unit test framework. So the next level would be a hardware software integration test. So that's the smallest possible hardware in the loop test. So you test your system under test is the microcontroller, including the complete software, including the drivers and so on. And that's not so easy to do. You usually cannot really use a unit test tool for that. Next level would be a big hardware in the loop test. So for example, including the power electronics, the motor, actuators, and so on. And in the end, you have a system test, which takes the complete system in the scope of your test. So your system under test is the complete system. The problem is from top to bottom. A unit test is, you can run it very fast, very often. It's inexpensive to produce. It's easy to automate and so on. And a system test is the opposite. It's usually slow. You do not run it very often because it's expensive or it's hard to automate. So that's the problem. You need at least 2 or 3 of those levels to really test your system. But the earlier you test your system, the better. So now let's have a look at what do you need to test a system or a component under test. So this can be a unit in C code. This can be a class. This can be a complete system. Whatever it is, you need 2 things. You need test cases that describe what you want to trigger and what do you expect. And you need, and that's what most testers forget at the beginning, or sometimes also the managers, you need to simulate the environment. So for a unit test, you get away usually with stubs and mocks. So you need to satisfy the interfaces that are called by your system under test. At least they need to return something that makes sense. And with a synchronous unit test is usually synchronous, you get away with stubs and mocks, so you really only satisfy the interfaces and maybe give back something that makes sense. The problem is the further you go up, the more asynchronous elements you introduce in your system. So for example, for a integration test or a system test, usually they are asynchronous, so many things are happening at the same time. And in order to really satisfy the interfaces, you do not get away with stubs and mocks. You need closed loop or open loop simulation. So for example, if your system controls a motor, you need the motor simulation, because you do not want to attach the motor, because then you cannot really test the system. But with a simulation, you can bring the system into any state you want. So you need a closed or open loop simulation, usually both, to really test your system. And asynchronous test cases, of course. So you need more than test cases. Now, let's have a look at a closer look at the hardware-software integration test. For a unit test, you can use model-based testing approaches to generate test cases and so on. But the real power of model-based testing is on the higher levels usually. So the main goal for a hardware-software integration test is, for example, not to test a single component, like a motor control, but the integration of the component with the software system, including the drivers and the electric signals. You can put, by using simulations, you can put your system in almost any state to test it by changing the simulation for failure injection. So you can not only test the happy path, but also the unhappy path. And this enables a very high degree of automation, speed, and depth in your test process. Now let's have a look at an example. Let's take this example again from before. We are looking at the microcontroller, including the complete software stack as it is in your application, including all the drivers as a black box. Now we are testing at the pins of the microcontroller. So for example, if you want to test a temperature shutdown for a shutdown path test for the temperature shutdown, for the motor control, for example, we provide an analog value. We inject the analog value as an error. So temperature too high, too low, that's easy to do with, it's just an analog signal. And then something magical happens in your software, because it's a black box test. Something happens inside, so the events are cascading through your system. The error control does something, the motor control is supposed to stop, and so on and so on. And in the end, what I want to test, or what I want to verify, is that the effect should be that the PWM is off after 100 microseconds. That's important, because I want, in case of an error, the motor to stop. It might be a safety critical application, or even for if you just want to achieve robustness, it's important that the motor stops after an error. And the other important thing is, for example, that you want to see the right CAN error message on the CAN bus, because you need to inform other systems. So those are two critical things you want to test by injecting this temperature that's too high. So how do we do that? First of all, if you have a motor control system, for example, you need a motor, you need to attach a motor. If you do attach a motor, you cannot really test very well and not automate it. It's not repeatable. It's really hard to automate. You can only test the happy path. If you want to test the unhappy path, you have to destroy the motor or whatever. So it's better to work with the simulation. So in this case, for example, we have a BLDC motor integration test. So we simulate the motor control, the motor, the hardware motor. So the motor control produces 3 PWMs. The plant simulation simulates the motor and the speeds 20,000 times a second or something like that. And it generates 3 Hall signals. That's the response a real motor would give you as well. So the motor control is not running against the real motor, but against the simulated motor. So you need, in this case, you need a closed loop simulation, because if you have an open loop simulation, if you just play back the signals, your control system does not work. It immediately goes to infinite or to 0, and a real closed loop controller works like that. So the plant simulation needs to really simulate the motor. It's not as hard as it sounds. It's relatively easy to do, but of course it's effort. But once you have that, you can bring your system into any state you want. So let's have a look at. So that was a model for environment simulation. Let's have a look at typical models for test case definition. So a typical test case definition model is a classification tree. It's good for structure development, analysis, and development of test cases, to find out about your equivalency classes, boundary analysis, or you decompose your system into components you want to write test cases for, and so on and so on. Typical example would be the unit test tool TESI that has a classification tree editor. And it really helps also with the analysis for safety relevant tests. Very nice method. Another typical example for test case definition are state transition tests. It's a method defined or taught also in the certified tester trainings, and so on and so on. It enables you a black box description of expected system behavior. And by using a code generator, you can really derive very fast the needed test cases to cover the happy and the unhappy paths in your system. So you get really a lot of relevant test cases with low effort, and it's very good for robustness test, and it's also part of some safety standards and so on. So the third method I want to introduce are sequence diagrams. Sequence diagrams can be used to describe test cases or to document test cases. It provides a very nice graphical view on test cases and the test execution. And it's really easy to understand also for non-developers or non-testers. Very often you design, especially on system level, the test cases together with the system developers. And they might not have a good idea about software development, but they have a really good understanding of your system. So in that case, sequence diagram is really nice to work together between the different groups of people. So those are typical examples for models for test case definition. So now we go to models for environment simulation. Also only examples, but very typical examples. You need them for integration and systems tests, usually, for example, hardware, software in the loop, and so on. So one typical model technique are state machines. So for example, state machines, yes, you use them for designing your software, but you can also use them for defining your environment simulations for state and event-based systems. Or also you can use them to implement interface protocols that are needed for test cases. So a state machine is a really powerful mechanism to define environment simulations. And another typical modeling technique is data flow modeling. For example, for environment simulation for continuous or closed loop systems. So state machines for event-based systems, data flow modeling for continuous systems such as a motor control or a environment simulation for a battery system. In this case, that's a Simulink model for a system, and part of that, the hardware here, this could be an environment simulation for your system under test. So those are typical techniques. Now I'm going to focus on the state transition testing on a piece of paper first, and then I'm going to introduce you or tell you how you can do this by using tools. So let's have a look at the state transition test. So with the state transition test, you define, you describe the black box behavior, the expected black box behavior of your system as a state transition diagram. So it's not the state transition diagram you use to generate your application or design your application. It's really a completely redundant approach where you just design the test case. So now let's design a state transition test. As at the beginning, you're always in the state motor off in a motor control system, then you turn the motor on. And then you have, for example, two different possibilities. You can change the speed and stop the system, or you can break the system. You can, and then you want to change the mode. Yeah, you go into mode 1 or you go into mode 2, and then the end. Then and now the question is, how does this help to design test cases? So if you want complete path coverage for all the paths in your system you've designed just now, you can do this on a piece of paper. So for example, you derive the first test case from initial to end. Every path from initial to end is potentially a test case. So you need one test case to cover the left side, and the second test case to cover the right side of your paths. Now I've covered all the states and all the transitions in my test description here. But what I do not cover is, for example, I want to change speed in mode 2, or I want to brake in mode 1. So in order to do that, I need a little bit more. So for example, I need this green and this red test case. They cross over here, and now I change speed against mode 2 and brake against mode 1. And I also can introduce cycles, for example. And now it starts to get more and more complicated, especially if the models get bigger. So you can do this really good on a piece of paper for smaller test descriptions or for lower combinatorial effects and so on. But if you really wanna use this method for robustness tests, for safety tests, it's good to have a tool for that. So I'm going to show you how this works with our mini-hill environment with a code generator. So you design the state transition test in the modeling environment. So that's what you need to design. And now we generate all the needed test cases to cover all the paths from initial to end, including the cycles, according to a certain metric. So for example, end switch 1 now generates 15 test cases to cover, for example, all the combinations of changing speed with all the combinations of change direction, brake, start, stop, and so on. So that's a very typical small example. So you have the formal description of the black box behavior of the system as a model, helps a lot. And then we generate the needed test cases as C code or as test scripts for path and data combinations. And you get the documentation for free. That's really nice to have, because if you run into an error, you want to know what your test system did. An example where we use this is the mini-hill hardware and software platform. So the idea is to test the system under test here. That's an STM32 microcontroller, and we test at the pins of the microcontroller over the signals. We connect the signals on the microcontroller over this patch panel with our test system. And here we have all the environment simulations and the test cases running, and they are modeled. So we have the models to describe the structure and behavior for the simulation and the test cases. Then we generate the test system directly as C code, and then it runs on this platform. Here we have, for example, not an STM32, but an Oryx processor from automotive project. And then we generate the log files, and we transform them into reports. And you can see the reports are also models, because we, as human beings, we understand those models better than plain text logs, for example. So we're using it to design test systems as well as to analyze the errors, for example, we found. And then we learn and iterate. Now I give you a little demo of an example test system. It's a very typical system, a BLDC motor control that generates 3 PWMs to control a motor. The motor is completely simulated. The simulation runs with 20 kilohertz or something like that, generates 3 Hall signals as digital outputs, because the motor controller then is able to control closed loop the simulated motor. And we also have a temperature sensor as an analog value, and over UART we control speed, or we get back information of the system, error messages, and so on. And now since it's only signals, and in simulations, we can simulate anything we want. We can break the system, we can bring it into any state where we want to test something. So now I'm going to make a little demo. So let's dig into a typical test model. So as you can see here, we describe the structure of my test system. So we have the IOs of the test system. Here we have the simulation, a motor temperature simulation that transforms degree centigrade into an analog value, 3.3 or 5 volt analog value. Here we have the motor simulation. For this, in this case, for the motor simulation, we use again a model, a state transition diagram, but to implement the environment simulation. That's, for example, if I get a new PWM value, I calculate the new speed, and I tell the whole generator, the IOs at the whole generator, what it has to do, and then it generates the 3 whole signals according to the actual speed. That's on the structural level. Here, the whole generator is attached here, and now it generates the 3 digital outputs. So that's where we use models, and it's much faster to use a model to describe this. You can also use a Simulink model to generate the code for the environment simulation, for a plant simulation, for a motor control, and so on. And in the end, you need a test case on top of that. Now with those 2 levels, our system under test already is able to work correctly against the simulation. And here we have the test cases. So test case again is a model, textual model in this case. But as you can see, directly attached to the textual model. So for example, let's have a look at a certain step, check speed. You already get, that's the generated diagram. You get a generated diagram that tells you as sequence diagram what your expected behavior is if you go 1 level up. So for example, in a test sequence, you see it's more complex, of course, and in a test suite, you see the complete test suite with all the test steps, all the sequences, and so on. So, but that's a specification. Now let's have a look at the state transition tests. Let's have a look at a little state transition test example. So here I have the state transition test. Again, it's a model. In this model, in the state transition diagram, you can tell at every step what it's supposed to do and what it's supposed to test. So path 1, for example, is a certain action and reaction that tests something. So that's trivial. I can generate 1 test case out of that. So if I show you the test case, the generated test case, that's 1 test case, and that's the sequence diagram, the specification for this test case. So now let's assume we want to add another path to the, just a second. So I want another path to state 2. Let's add the path 2. And we do the same with the path with the state 3. So I go to state 3, also over path 2. So now if I generate the, just a second. If I generate the system, you can see that we have now a couple of more test cases. So now we have 3 test cases. So those are the 3 test cases. But for example, we do not test path 2 versus path 2 here. So we do not test a certain path here. So this versus this. So in order to do this, I can raise the metric here from end switch 0 to end switch 1. And again, I generate the test case, in this case, documentation and the code. Just a second. Now suddenly I have 4 paths. Path 2 has been added because end switch adds a higher level of combinatorial paths, and and helps me to generate the complete coverage for that. So last thing I want to show you is when I'm in state 3, I introduce I return to my let's say to state one. State one. Here again, you can see what changes. So I go back here, and now I'm raising the coverage, more combinatorial states, and so on. I'm generating the test cases again, and suddenly you see we have not 4, but in this case 12 test cases to cover what I've defined. Now, last thing I want to show you here in the model is a real-world test case. So a state transition test for this motor control demo system. So for example, here I can model the equivalency classes you've analyzed, or the border values, boundary values. So in this case, I would maybe add the boundary value 1 and the boundary value 99 or 100 or whatever are your boundary values. Here, see, now suddenly you have a couple of paths more, and instead of having 15 test cases, if I regenerate this, you have a couple of more test cases now. Let's have a look at this. Now suddenly you have 25 test cases. If I want more combinations to find, for example, race conditions, sporadic errors, and so on, you can really stress the system. Let's go further up with the metric here. Now I'm generating much more test cases. Let's have a look at this. We had 25, and now we have 163 test cases, and much more different paths, much more combinations of parameters and orders of execution and so on. And it's everything asynchronous, but in order to do this, you need the environment simulation and the code generator for those test cases here. So now, last but not least, we can run the test system. I'm connecting with my the generated system here with my system, with my test system. System under test is this microcontroller. Here, see all those signals I've defined before. So UART, PWM, the Hall sensors, and so on. And now I'm going to run the test cases. In this case, I only run the first 15 here. So I'm running the test cases. I'm pulling a plug while the system is running to introduce an error. So now you see the system ran and it failed. Yeah, of course it failed because I ran into a problem. So now, of course, the other tests are running as well. And now I can click on the problem, for example, and go directly in my test environment directly to the step where my system actually failed. So that's very important because now I can analyze in my sequence diagram and of course in my application where my problem is. I can reproduce the problem if let's regenerate this with another metric here. So let's get this metric back to the original one here. So, and maybe because then it does not run as long as it does. So now I'm going to run it again, and suddenly it's okay, everything okay here. Yeah. So now the test is okay, and yeah. So that's that was a little introduction about model-based testing. You need to generate test cases, or you need to create test cases, but you also need to stop or simulate the environment, and models can help you with both in a very nice way. There are tools out there that can do this. So model help with working on a higher level of abstraction. Doesn't matter if you work on an application or on a test case. Higher level of abstraction, if it gets more complex, is very useful. It's very good to understand and communicate problems and solutions better. And it's very good to derive and generate test cases in a more structured and efficient way. Especially if you've seen with the simulations and with the state transition tests, you can really be very effective and by using code generators for this kind of problem. And by doing that, you speed up the development of environment and plant simulations by using those models. So, yeah, thank you for your attention. I will answer the questions via email afterwards, and I hope you enjoyed the webinar. Hope to see you soon in the next webinar, and have a nice day. Bye-bye.